So Jacqueline, what'd you get to look at since the last time we were at?
I'm working on a few lessons,
Like which one?
limits continuity, say about halfway through the whole thing. But
Now,
I just looked at parametric function.
we're gonna need the practice at the end of that section.
Me? And not. I just watched the video.
I was doing a practice question things. And I think there's like a unit test at the end or something.
Sounds right. Let's see, there's a couple of interesting things on page 76 about a particular parametric curve, a cycloid.
Cycle.
Page 75, 76, the cycloid.
I'm a mess, Mr. Rutherford.
Yeah.
So like it says, the cycloid,
I'm a train wreck.
one way it can be defined is as the path of a point on a circle that's rolling along a line. So you pick a point on the rim of your tire as the tire is driving. That point's path is a cycloid. Looks like shape in the middle of page 75.
Oh, you can use spider crabs. I like those. We had them last year or 2 years ago. Here.
Very good kit and toy and learning.
It's just looks like.
And it mentions on page 76 a couple of interesting things about this cycloid shape. One thing to know about it is that, as it says, if you have a bowl in the shape of an inverted cycloid, and you get like a marble and put it on the side of the bowl and release it, it will take the same amount of time to reach the bottom regardless of how high you start. Because higher up the walls are steeper, and so the marble accelerates more rapidly from the higher starts, but it has farther to go. The walls are flatter lower down, but it doesn't have as far to go.
So it cancels out.
It does. Christian Huygens, who was a physicist interested in optics and also an astronomer, proposed that actually it would be better if you're going to build a pendulum clock. It would work slightly better if you could make the pendulum swing in a cycloid, because then the period would be truly independent of amplitude. With a simple pendulum, the period doesn't depend on the amplitude as long as the amplitude is pretty small, but for larger amplitudes it does become dependent on it. But if the swinging path is a cycloid, then for this reason it's actually totally independent regardless of amplitude. But it's actually pretty hard to make something swing in a cycloid instead of in a circle arc. You basically have to do something like have a flexible rope down to the bob and then have sort of a barrier in a curved shape to either side of it, so that as it swings, the pendulum gets shorter. Because part of it is in contact with this, like after it swings
Is there
a
an
little ways,
example of something like this?
it would be
that
like
we've seen
this.
before?
An example of something like this that we've seen before.
Or like that we would recognize?
Cause like I remember a question on the test in final physics where you couldn't like generate energy just by like, it couldn't like swing like that or something. Because you have no like infinite energy.
Okay,
Or you can't.
there was a question about perpetual motion machines.
So yeah, that was.
You're not going to be able to generate infinite energy by something moving around in a cycle. That's not what this is about. This is about changing how long the pendulum is at different points in the swing in a way that makes it swing with the same period no matter how far it's displaced to the side. Well, anyway, there are exercises at the end of section 1.7 about different kinds of parametric systems and some different examples. It shows like a graph of x of t and a graph of y of t And it asks you to figure out the combined graph of the path. That's worth looking at just a little bit. Look at page 77 there. So what, this is number 22. It's like the upper left quarter of page 77. So it gives you labeled A, B, C, and D are paragraphs of x of t and y of t. And the labeled Roman numerals 1, 2, 3, 4 are resulting paths. It's asking you to match them together. Are we short a textbook today?
Yes.
Short two textbooks today?
Yeah,
Mine's like,
Not terrible.
I unpacked my bag,
Yeah,
because
I
I
know.
use it to go hiking.
Well,
Oh, okay. So A and B are a pair, and you're trying to match which one of, okay, I thought you was
if the
like,
particles
pick
x
one of
coordinate,
these two to make.
yeah, if the particles x and y coordinates follow those functions over time, then what will the path look like? So these are parametric systems, and these are 4 possible resulting paths. The idea is to match. Let's see. From time 0 to 1, x goes from 1 to 2 to 1. Yeah, looks right. And then y goes from 0 to 1 to 0 to negative 1 to 0. Yep. Looks right. Anything kind of matching him.
Can you put the one across from it?
Okay, does it go with this? No.
C is with 4.
Yes.
Yes.
Yeah. Okay. C goes with 4. So x goes from negative 1 to 0, or negative 2 to 0 to 2 to 0 to negative 2 to 0 to 2.
Mm-hmm.
So that's x equal to 0. It's like negative 2 to 0 to 2 to 0 to negative 2 to 0 to 2. So as you sweep across these two, it's going to trace this path this way. Notice that all the y values here are between 0 and 2, and all the y values here are between 0 and 2.
This one, is this one A?
These two together are this one.
Yeah, this one.
Oh, yes.
Oh, yes.
Yes.
I love myself.
1 to 2 to 1, 1 to 2 to 1. And
No, this one's this one because it has the most lines. There's that.
there, yes.
So, because I don't know, 0 to 2 to 0 to 2 is that's not
Yeah,
bad.
yeah, in different phases. This is like a spirograph.
Yeah. 2 to 0 is negative 2 to 0. And that's just the odd one out. It's gotta be it.
So notice there's this period where x hovers at 2 for a while, so that's going to be this segment. And there are 2 periods where y hovers at negative 2. It's like beginning down here, and then increasing, and then decreasing.
Oh, I like
So these are parametric systems. There's a function for x as a function of t and y as a function of t. And when you put them together, they make a path in xy space that a particle might follow. So some other things in this first chunk of the Khan Academy lessons. I see talking about continuity. Again, y'all defined this correctly before. It means the limit coming from the left and the limit coming from the right and the actual point are all the same. Y'all can talks about limits and asymptotes.
That's there's an asymptote that doesn't touch it. The limit is like
It
undefined,
infinitely
right?
approaches it to an infinitely close.
More and more closely, yeah.
Infinitesimal.
So,
Derivate.
It was derivate.
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 so let's see. Okay. Rational functions often end up having asymptotes in them. So let's see. What asymptotes will this graph have?
X equals
-2
Why do you say that?
We would make the denominators as well.
So it's definitely going to be undefined at those places. So the domain is going to be any real number except -2 or 5. It does not have asymptotes in both of those places, however.
Oh, no.
In one of those places, both the top and bottom of the fraction become 0. And when that happens, and it's with the same degree on the top and bottom, you don't have an asymptote, you have a hole, a single point. This
So
is
it
fine.
would technically just be 5.
Yeah, so
Yeah,
there's a
yeah.
point discontinuity at x equals -2, but there is a vertical asymptote at x equals 5. So if we graph it, we have a vertical discontinuity where x equals 5, and a vertical asymptote and an infinite discontinuity.
We did a chemistry test Thursday, right?
Yeah. Does this graph have a horizontal asymptote, and if so, where?
Where?
Let's refresh some of these things if they're not fresh. So if the bottom only goes to 0, then you get a vertical asymptote. If the top and bottom go to 0
Good.
with the same degree, then you get a whole point discontinuity. And then how do we know about horizontal asymptotes? When I say degree, that's a term from polynomial analysis. What's the degree of a polynomial?
The highest exponent.
Yep. So a rational function, a rational expression, it's a polynomial divided by another polynomial. So we can talk about the degree of the rational expression, the overall degree. And that's going to be the degree of the top minus the degree of the bottom, because it's division. Yes. What's the degree of this one?
0.
Nice. So if a rational function has an overall degree of 0 or below, it will have a horizontal asymptote. If it has a degree, so if it has a negative overall degree, Jacqueline, what does that mean? How do you recognize if a rational expression has a negative degree overall?
I can't remember.
So I just said it's the degree of the top minus the degree of the bottom.
Yeah.
So the overall thing has a negative degree if there are more powers on the bottom than on the top.
Yeah.
If that's the case, it's going to have a horizontal asymptote at y equals 0. Because that means that as x gets bigger, in the long run, the fraction is going to get smaller. because there's bigger powers on the bottom than on the top. So the value is going to approach 0. So if the overall expression has a negative degree, it will have a horizontal asymptote at y equals 0. In this one, the degree is 0. So if it's a 0 degree rational expression, that means that in the long run, the powers of x are going to kind of cancel out. The top and bottom are going to grow at about the same rate. And so it's going to stabilize at a fixed ratio. And what you're going to get there is the ratio of the leading coefficients. That's right, it'd be 2 in this case. So if x were 70 trillion, then we would have that number here, 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 and here, and they would basically all cancel and just leave us a 2. Yeah. So it's going to be the leading coefficient of the top divided by the leading coefficient of the bottom is going to be a horizontal asymptote. So horizontal asymptote at the ratio of the leading coefficients. So in this case, there's going to be a horizontal asymptote at y equals 2.
So if the top was like 4 and the bottom was like 2, then it would be a 2.
Yes. It's going to approach y equals 2. What are this graph's x-intercepts? Or intercept or intercepts, depending on how many you think there are.
-2.
No. If the top went to 0 and the bottom didn't, there would be an x-intercept. Since they're both going to 0 there, it makes a hole. So it's just 1.5
Oh my goodness.
is when the top would be 0, but the bottom not 0. So the graph is going to have
y equals mx plus b, the b. X-intercept.
the b is the y-intercept. It would be like here at 1.5. And then the y-intercept is what you would get when x is 0. So you just plug in zeros for all the x's, which makes it a lot simpler. So then let's say -6 over -10, which reduces to positive
4/5.
3/5. So that'd be right about here.
Math does not work.
And so then looking at the asymptotes, you can maybe kind of see that the overall shape of this graph is going to be kind of like this. Kind of like that. And there's that hole when x is -2. What's the y-coordinate of the hole?
-1/2.
1, I think.
Can you have a hole on
It is
the
actually
asymptote?
1. Nice, Jacqueline. How did you get that?
I don't know.
Because you plug in -2 as x, and you ignore the ones that are already out. And then it's -7 over -7, which is 1.
I could choose smarty pants.
The hole is just where the curve would have gone if these two parts that are the same weren't there. So like having this on the top and bottom, the only effect that has on the picture is to take out that one point. Nothing else changes. Every other part of the graph is going to be as though those weren't there at all. And so if those weren't there when x was -2, the y-coordinate would be 1. How did I know that when I came down this asymptote that it would come from the positive infinity on the other side? Because it doesn't always. Sometimes it could like dive down and then come up from negative infinity again.
So why doesn't it?
How do you know which one is which? How do you know whether these are going to go opposite ways or the same way? as the curve approaches the vertical asymptote from the two sides.
I know this, I just watched a video on it.
Does something to do with like the dome?
No. It's about the multiplicity of the zero in the denominator. This is to the first power right now. So when x is 5, that's 0. If x is slightly more than 5, then it's a small positive number. But if x is slightly less than 5, then it's a small negative number. And the result of that is that it sends the two tails in opposite directions. But if on the bottom it's x minus 5 squared, then to either side of it, it would be a very small positive number. And so they would both go the same.
Okay.
So the thing that's going to 0 on the bottom, if it's positive, if to either side, if on one side of the asymptote that thing is a small positive value, on the other side it's a small negative value, then they're going to go opposite ways. But if it's positive on both sides or negative on both sides, then they're going to go the same way. So for a polynomial expression, a polynomial factor, it's going to be about this exponent here, about the multiplicity of 0. If it were something else like, so maybe if we had like the sine of x on the bottom, and so it went to 0 at pi, and we get a vertical asymptote at pi, would they be the same or would they be opposite? So if I graph, y equals 1 over,
Oh, for
sine
sine, that
x.
would be, it would be the same.
so if over here is pi, then should it like go up and then come from below, or should they be the same? Should they both be going up, both down, or one up, one down?
No, they should both be going down.
Why do you say?
Because if you look at the sine graph, when you hit pi, it's at 0, and then
So if you're slightly to one side of pi or slightly to the other side,
they'll both be negative.
about this point here, one side of it's positive and the other side of it's negative. So the result is that the graph is going to go like this.
Okay.
We're actually talking about the cosecant graph here. It behaves like that. But so something that wouldn't do that would include, well, like I said, just something with an even power on the thing that's going to 0. Yeah, so I mean, a graph like, if I say 1 over x squared, the graph looks like this. Because on either side of 0, that denominator is positive. So some things about asymptotes. Oh, and if the degree is positive, then you don't get a horizontal asymptote at all. Rather,
You're right, Stevie.
insightful. If you have a positive degree, then toward the ends, the graph approaches whatever you get when you do the long division. So long division gives the end behavior.
Or how many years it's been since I've done long division?
Remember that really one when it was really, really long division?
What?
We made like a little bracket. It had like a little bracket here, and it was like all the numbers, and you did something to all the numbers down here.
No.
Okay,
Synthetic division,
I
maybe?
think so.
Oh,
It changed
It's
that.
not long division. Oh,
And it only worked in certain cases or something.
Yeah,
I don't
Or
like
like-
synthetic division, just don't want division.
I just use my calculator.
Nice.
Ow.
So, like, a quick example of what I'm talking about with that is that if you have something like this, y equals this. So it's going to have a vertical asymptote here. What about at the ends? What does the end behavior look like? Well, you can find out by long division.
I
Otherwise,
remember
like,
this.
Factoring out
This goes
x
here.
minus 1 pretty much.
Well, if x minus 1 is a factor, yes, but then we could just simplify it. In that case, there would be a hole. But if it's not, there's going to be a vertical asymptote, and then we're doing this with x squared minus x, parentheses, subtract, 6x minus 2, 6x minus 6, parentheses, subtract, 4.
Wait, what? How'd you go from plus to 5 minus x to 6x?
Minus x.
Oh, okay, never mind. I got it now.
And so there's remainder 4, and so this is plus 4 over x minus 1.
Dope.
But the point is then as x gets big in either direction, this part becomes really small, and the graph becomes y equals x plus 6.
Mhm.
So zoomed out, it just looks like the graph of y equals x plus 6. But where x equals 1, it goes like this. It's going to go like this. It's going to have a little vertical asymptote at 1. But other than that, the graph looks like y equals x plus 6. So whenever you have a positive degree rational function, if you zoom out, it looks like the thing you get when you do the long division. Okay. Well, today's Monday. For Wednesday, finish looking through this first section of Khan Academy. It talks about the intermediate value theorem. That's something I like to name drop a little bit on the test. It's not hard to understand. It's not hard to do. It's just a recognition thing. So look at the section on the intermediate value theorem, and that should wrap up the kind of limits review stuff, limits and continuity review. And then we'll talk differentiation.
Derivatives.
Derivation.
Derivation. What's the real word for that?
Differentiation.
I like derivation. Never made that one stupid.
I was getting it, yeah.
What are you doing?
This is my spot.
He was like so zoned.
This is my
in.
gas.
What are you
Look, you
doing?
can try.
Way to be assertive, Sophia.
It's chapter 4.
Okay.
Why are you in
Hey,
here?
didn't it talk about
Hey,
that?
I need a chair. Is that my chair?